Our journey begins long, long ago. Think of our earliest ancestors gathered around a crackling fire, looking up at a sky filled with countless stars. They didn't have telescopes or fancy equations, but they had something just as powerful: curiosity. They were the first physicists. They observed the world with wide-eyed wonder, noticing the predictable dance of the sun across the sky, from sunrise to sunset. They saw how shadows stretched and shrank as the day progressed. A simple observation that is, at its heart, about the straight-line path of light. This was the very beginning of our quest to understand the cosmos. A quest driven by the simple act of looking up and asking, why? These ancient stargazers became the first timekeepers and navigators. They learned that the positions of the stars could guide them across vast, featureless deserts and oceans. In places like ancient Egypt and Mesopotamia, they built massive structures, like the pyramids and ziggurats, with an astonishing alignment to celestial events. They tracked the phases of the moon and the changing of the seasons, creating the first calendars. This wasn't just idle observation, it was a matter of survival. Knowing when to plant crops and when to harvest was a matter of life and death, and the universe itself provided the clues. They were decoding the fundamental rhythms of planet Earth. In ancient Greece, this spirit of inquiry took a giant leap forward. Thinkers like Aristotle and Archimedes tried to move beyond just observing. They wanted to explain. Aristotle attempted to create a complete system to describe why things fall to the ground and why the planets move in the heavens. While many of his ideas were later proven incorrect, his ambition to find underlying principles was revolutionary. Archimedes, on the other hand, gave us one of the first eureka moments. By noticing the water level rise as he stepped into his bath, he uncovered the principle of buoyancy, a fundamental concept in physics that we still use today to build massive ships that float on water. This was a time of grand ideas, where philosophy and science were intertwined. The Greeks imagined the world was made of fundamental elements: earth, water, air, and fire. They debated the nature of matter, with some, like Democritus, proposing that everything was composed of tiny, indivisible particles he called atoms. Though they lacked the tools to prove it, this was an incredible intuitive leap, a whisper of a truth that would take more than 2,000 years for science to finally confirm. These early steps, full of mistakes and brilliant insights, laid the very foundation upon which all of physics would be built. They taught us that the universe was not just a chaotic mystery, but a puzzle that could, perhaps, be solved. For centuries, science simmered with these ancient ideas. Then, in the 17th century, a man was born who would change everything. His name was Isaac Newton. Imagine a world where the motion of a falling apple and the orbit of the moon were seen as two completely separate, unrelated mysteries. Newton, with his brilliant mind, saw the connection. He realized that the same force pulling the apple from the tree to the ground was also the force keeping the moon locked in its eternal dance around the Earth. This force, he called it gravity, was universal. It wasn't just an earthly phenomenon, it was a cosmic one. This single idea was breathtaking in its scope. It unified the heavens and the earth under one set of rules. Newton didn't just have the idea, he gave us the mathematics to describe it. He developed a law of universal gravitation, an equation so powerful and elegant that it could predict the motion of the planets with incredible accuracy. Suddenly, the universe seemed less like a place of divine whims and more like a grand, intricate machine, a clockwork universe ticking away according to predictable, knowable laws. His work gave humanity a newfound confidence in its ability to understand the cosmos. But Newton didn't stop with gravity. He also gave us his three laws of motion, the bedrock of what we now call classical mechanics. The first law tells us that an object will stay still or keep moving in a straight line unless a force acts on it. The second law gives us the famous equation F equals ma, linking force, mass, and acceleration. The third law, simple yet profound, states that for every action, there is an equal and opposite reaction. These three laws explain why you feel a push when you jump, how a rocket propels itself through space, and why a ball curves when you throw it. With these laws, humanity could suddenly calculate the trajectory of a cannonball, predict the tides, and even discover new planets just by observing tiny wobbles in the orbits of known ones. Newton's work, compiled in his masterpiece, the Principia Mathematica, was more than just a scientific text. It was a declaration that the universe is governed by mathematical laws that are accessible to the human mind. He provided the toolbox, the language, and the framework that would dominate the world of physics for the next 200 years, building a magnificent edifice of understanding on the foundations laid by the ancients. As the 18th and 19th centuries unfolded, physicists began to explore a new realm of mysterious, invisible forces. For ages, people had known about the strange crackle of static electricity and the curious pull of lodestones, natural magnets. But these were seen as little more than curiosities, parlor tricks. Scientists like Benjamin Franklin, with his famous and incredibly dangerous kite experiment, started to show that the spark you get from rubbing a cloth was the same stuff as the terrifying lightning that split the sky. This was a crucial step, linking a small-scale phenomenon to a grand natural force. The study of electricity was beginning in earnest. At the same time, others were investigating magnetism. They mapped the invisible fields around magnets using iron filings, revealing elegant looping patterns of force. A pivotal moment came when Hans Christian Ørsted, during a lecture, noticed that an electric current flowing through a wire caused a nearby compass needle to move. It was a complete accident, a serendipitous discovery that revealed a deep and unexpected connection. Electricity could create magnetism. This discovery electrified the scientific community, opening up a whole new avenue of research. The universe had another layer of secrets to reveal. The next piece of the puzzle was put in place by Michael Faraday, a brilliant experimentalist. If electricity could create magnetism, he reasoned, could magnetism create electricity? Through painstaking experiments, he proved that it could. By moving a magnet through a coil of wire, he could generate an electric current. This principle of electromagnetic induction is the foundation of almost all the electricity we use today. It's the reason power plants can generate the energy that lights up our cities and powers our devices. Faraday, with his incredible intuition for picturing fields of force filling empty space, laid the conceptual groundwork for a grand unification. That unification came at the hands of James Clerk Maxwell. He was a mathematician who took the experimental findings of Faraday and others and translated them into a set of 4 beautiful, powerful equations. These equations described electricity and magnetism not as separate forces, but as 2 sides of the same coin, electromagnetism. But Maxwell's equations predicted something even more astonishing. They showed that disturbances in this electromagnetic field would travel through space as a wave, and the calculated speed of this wave was exactly the speed of light. In a stunning revelation, he had discovered that light itself is an electromagnetic wave. The invisible forces were now connected to the most visible thing in the universe. The beautiful clockwork universe of Newton and Maxwell seemed nearly complete, but as the 20th century dawned, cracks began to appear in this perfect picture. A young patent clerk in Switzerland named Albert Einstein was about to shatter it completely. He thought deeply about the nature of light and motion, and his thought experiments led to a revolutionary idea, the theory of special relativity. It proposed that the speed of light is a cosmic speed limit, the same for all observers, and that as you approach this speed, time itself slows down and space contracts. It was a mind-bending concept that changed our fundamental understanding of space and time. 10 years later, Einstein presented an even more radical theory, general relativity. He reimagined gravity not as a force pulling objects together, but as a curvature in the very fabric of space-time itself. Imagine a heavy bowling ball placed on a trampoline. It creates a dip, and a marble rolled nearby will circle the dip, appearing to be attracted to the ball. Einstein proposed that massive objects like the Sun do the same thing to space-time, and planets like Earth are simply following the curves. This elegant, beautiful theory has been confirmed again and again, explaining everything from the bending of starlight to the existence of black holes. While Einstein was rewriting the rules of the very large, another revolution was brewing in the world of the very small. Physicists studying atoms and particles found that they didn't behave according to the familiar laws of Newton. They behaved strangely. This led to the birth of quantum mechanics. It's a world where particles can be in multiple places at once, where observing something changes its reality, and where energy comes in discrete packets called quanta. It's a probabilistic universe, governed by uncertainty. a stark contrast to Newton's predictable clockwork. This theory, despite its weirdness, is arguably the most successful scientific theory ever, forming the basis for our digital world of computers and lasers. Today, physics stands at another fascinating frontier. We have two incredibly successful theories: general relativity for the cosmos and quantum mechanics for atoms. But they don't play well together. Finding a single theory of everything that unites them is the holy grail of modern physics. We are also grappling with giant mysteries like dark matter, an invisible substance that seems to hold galaxies together, and dark energy, a mysterious force that is causing the expansion of the universe to accelerate. The story of physics is far from over. From our ancestors gazing at the stars to today's scientists peering into the origins of the cosmos, the quest continues, driven by that same simple and profoundly human sense of wonder.